So we've learned about lines in 2 dimensions. What about lines in 3 dimensions? Well, by now we know that vectors can be expressed in 2 dimensions, something like that, or in 3 dimensions, something like that, right? Vectors can have any dimension. So if we look at our equations of our lines in 2D, we realize that all the ones that contain vectors, we can really just extend that to 3D. Now, the ones you won't see here are y equals mx plus b. There's no sort of 3D form of that type of equation of a line. And also the other one you don't see here is this. Standard form, or Cartesian form as it's sometimes called. We don't see a Cartesian form of a line as well. So, and there are very good reasons for that, and we'll discuss that in class. But for now, all you need to know is that the vector one, it's the same as the 2D vector equation of a line. It's just got a third part. It's got a z as well as an x and a y. So the form, the general equation looks like that, x, y, z. X naught, y naught, and z naught is the starting point on the line, or wherever, so your reference point on your line. T is the parameter, same as in 2D. And then ABC is our direction vector. Right? So we have 3 parts to a direction vector and not 2. For our parametric form of our line, we just split up the x, the y, and the z components, same as 2D. And the symmetric part, now instead of 2 parts to the symmetric equation, we have 3 parts to the symmetric equation. And we can solve for it in the exact same way that we did in 2D, just isolate the t in each of these equations and set them all equal to each other. Keep in mind that in this equation, the thing that's subtracted from the variables is the point on the line, and the denominators should be the direction vector. Okay, let's dive into some questions. A line passes through -3, 5, and 2 with a direction vector of 1, 2, -1. So just to draw a quick sort of diagram of this line, if this is our line going through 3D space, we have a point on the line and we call that P, -3, 5, 2, and we have a direction vector from that point, and we call that direction vector, I don't know, in this case, what do we call it up here? We call it M with a line on top, because it's sort of like a slope. A direction vector is sort of like a slope, not exactly, but it's sort of like, it tells you what direction to go for a vector. 1, 2, -1 is our direction vector. So we can write the equation of this, if we use this one up here as reference, it's just going to be xyz equals the point, -3, 5, 2, plus t, our parameter, 1, 2, -1. Nothing fancy about that. We could also replace this xyz with just an r. Usually r represents a line, an equation of a line. So, next. Does point Q lie on this line? How could we figure that out? First, we can see that basically this is the x, the y, the z, obviously. This is x, y, and z. So in our equation here, that would sort of be our x, our y, and our z, right? That we could plug into our equation of our line. And then what could we solve for? Well, if we write out sort of the parametric equation of the line, we can see that each equation will have a t in it, and we can maybe solve for t. So let's try that. So x equals parametric form, -3 plus t. Y equals 5 plus 2t. And z equals 2 minus 1t, or 2 minus t. Okay, so we can plug in our x, our y, and our z. And I want you to think about what's going to happen when we do that. So let's try this. So if we plug in 3 equals, plug in the x value of 3, -3 plus t. T is just going to equal 6. Okay, let's see what happens if we do that for y. 2 equals 5 plus 2t. If we solve for t, it's going to be I believe, -3/2. And then if we plug in z as -5, 2 minus t, t is going to equal 7. What do you notice about these 3 values? Well, they're all different. What should a t value be for an equation or for a point on a line. They should be the same. Remember what t is. T is a parameter, which means if we plug in values for t, it's going to spit out points on the line. So, for example, we're starting at this point here, negative 3, 5, and 2. If we plug in like t as 0.1, it's going to generate a point here. 0.2, it's going to generate a point here. If we plug in t as 0.3, it's going to generate a point here, etc. If we plug in t as negative 0.1, it's going to generate a point here, negative 0.2, etc. So basically, if we make t an element of real numbers, all numbers, it's going to generate an infinite number of points along that line. But the thing to remember is each of those points corresponds to one t value. So each point has its own distinct t value. Notice how these are 3 different t values, which means they can't be on the same point, right? They can't be, or the point can't be on the line, I should say, right? Because if they did, all the t values would be the same, because that would be the t value that generates that point. So that point cannot be on the line. Moving on. Next question. This question we're asked to find the vector between 2 points, 4, negative 5, and 3, and we'll call that A, and 3, negative 7, and 1. Right? So we have a line through these 2 points, right, in 3D space, and we want to find the equations of that line. Well, what do we need for the equations of a line? Let's go back over here. We need a point and a direction vector. We have 2 points actually, but we need a direction vector. How do we find a direction vector between 2 points? Well, we just got to find a vector between those 2 points, right? So for example, if we find vector AB, that is a valid direction vector for that line. We could also find BA, it doesn't really matter, but I'm just going to do AB. So vector AB, we can find that by subtracting the x, the y, the z coordinates. So 3 minus 4 is negative 1. Negative 7 minus negative 5 is going to be negative 2, right? It's like negative 7 plus 5. And then 1 minus 3 is also negative 2. Oh, and we usually do vectors as square brackets like that, so let's do it like that. So AB is negative 1, negative 2, negative 2, right? So that is a direction vector for our line. So we know that's the direction vector. If we want to express our line, we now know we could just do, I'll just squeeze it in over here, x, y, z equals point, and we can choose either point, right? Because either point can act as a starting point for that line. Let's just do A, so 4, negative 5, 3, plus t, negative 1, negative 2, negative 2. That is one possible equation of that line. There are an infinite number of possibilities for this, because we can choose vector BA, we can choose a different point, but this one is perfect. So that is the vector form of the line. Symmetric, we just read out the 3 parts separately. So x is going to equal 4 minus t. Oops, 4 minus t. Y is going to equal negative 5 minus 2t. And z is equal to 3 minus 2t, where t is an element of real numbers, obviously, according to our parameter. And this is the parametric form of the equation. Lastly, we're asked to find the symmetric form. So in each of these cases, I know I'm sort of out of room here, but I'm going to write off to the side. I'll write it in white so we can see it. We got to solve for t and then set them equal to each other. So the first one to set for t, set equal to t, it's going to be t is equal to, what's it going to be? 4 minus x. Or usually we like to write it with the variable first. So in that case, it would be t equals negative x plus 4. But we also usually like to write it with nothing in front of the x. If you look at the form of the equation, it usually just starts with an x, like that, like x, oops, do that, x minus x naught. So the way we could do that is we can pull that negative out, or factor it out. It's going to look like this. T equals negative x minus 4, right? But that doesn't really look like our symmetric form either. So instead, what we can do is we can actually sort of cheat and put that negative as a negative 1 in the denominator, like that, right? It doesn't matter. It doesn't change the value of the equation. We factored it out. We can just put that negative in the denominator. So that looks more like our symmetric form, right? We can do the same thing for the y. If we isolate y here, we're going to get negative y minus 5 over 2. And again, we don't want anything in front of that y, so let's pull out a negative. Negative y plus 5 over 2. And that negative, we can put that again in the denominator. It doesn't matter where we put that negative. So just for proper form, let's just put it down there. And then we can do the same thing for z. So t in this case is going to equal negative z plus 3 over 2. And we can factor out that negative, make that a minus sign there, and then move the negative to the denominator. So t equals z minus 3 over 2. So our symmetric form of the equation, going back over here, is just going to be x minus 4 over negative 1 equals, our y was y plus 5 over negative 2, and our z was z minus 3 over 2. Okay, and that is our symmetric form of the equation. Notice how, if we go back over here, we see from this equation, x naught, y naught, and z naught should be the three things that are subtracted from here. And if we look up at our point here, that makes sense, because our point was 4, negative 5, and 3, right? The opposite signs of these. And our direction vector was the thing in the denominator, negative 1, negative 2, negative 2. There we go. So it checks out. Next, write the vector equation for this line. So x minus 1 over 1, y minus 2 over 3, and z equals 3. So it almost looks like the irregular symmetric form of the equation, but it looks a little bit different. We got that weird z equals 3. Let's worry about that in a second. Let's first worry about the first two parts. They're a little bit simpler. So the way we turn a symmetric equation into a vector equation is we can remember that each of these things, we can just set them equal to a parameter like t. So we can do this. T is equal to x minus 1 over 1 as, one way of writing that equation. And then we can just solve for x to turn it into parametric form, right? Because parametric form is going to be nice. Once we have parametric form, it'll be really easy to get vector form. So to solve for x in this case, it's going to be, x is just going to be, if we cross multiply that one up, we move the 1 to the other side, t plus 1, right? We do the same thing for the y part. So y minus 2 over 3 equals t. And if we solve for y here, we're going to get, what are we going to get? 3t plus 2. So what do we do with this z? What does it mean if z equals 3? Well, think about it in terms of 2D. Let's just pretend this is a 2D problem for a second. In fact, let's just call this the x-axis. Let's call this the z-axis just to make it easy. We're flattening our 3D space into 2D space. What would it mean if you had a line that said z equals 3? Well, all that means, right, is that it's constantly at a z value of 3. It's horizontal at 3. Or another way to put it is that it's always at a z value of 3, or it's perpendicular to the z-axis. So notice how there's no t here, so there's no t to solve for, but it also is already solved for z. So that is our parametric form. It already is z equals something. We don't need to do anything with it. Now, this might look a bit weird, but again, remember, to get from parametric form to symmetric form, if we started with this and wanted to go back to parametric form, or symmetric form, you'd be able to solve for t in these two cases to get this. There's no t to solve for in this case. So that's why you just leave, in symmetric form, you would just leave it like this if there's no t to solve for. Okay? So anyways, how can we come up with the vector equation now? Well, you can sort of think of this third one as like 3 plus 0t, right? There's no t value. It's not affected by the parameter. The z-coordinate is not affected by the parameter, essentially. So to write out the equation, we could do x, y, z equals our point, and our point can be like this, 1, 2, 3, right, plus t, and the values are, the coefficient here would be 1, 3, 0. Okay? Again, if you remember that the denominator is just your direction vector in symmetric form, then you could sort of just go directly there. There's 1, 3, and then here 0t, there's no t, so you can just put a 0. And then our point is the values that you're subtracting from the top. Then you could also just straight up do it that way. So there we go, vector form of the equation. Last question, are the following lines collinear? Well, do we remember what collinear means? Collinear means essentially just the lines are on top of each other, so it's the same line. So if you had two lines, like for example, this line, and then you had a green line on top of it, collinear means they're the same line. So basically, can you prove that these lines are collinear or not? There's actually a whole bunch of different ways you can do this question. I'm going to just show you one way, which I think is a little bit interesting. Like, for example, you can find the direction vector and see if the direction vectors are multiples of each other, and then check the points. There's lots of different ways. I think this way is interesting. I'm going to start by just generating a point on the first line here. So this is one line, and this is the other line. We'll call this line A. Let's just label that. This is line A, and this is line B. Okay? How do I generate a point on this line? Well, obviously I could turn this into vector form or parametric form and then into vector form. That's sort of the long way. But I could also turn this into, or generate a point just by plugging in a value for x. If I plug in a value for x, I should be able to find the corresponding y and z coordinate. So I can plug in any value for x to find a point. I'm going to pick an easy value for x. I'm going to pick x as 5, because if I pick x as 5, it's going to be 5 minus 5, which is 0. So this whole thing's going to be 0. I think that's going to make it really easy for us. So I'm going to start off with x equals 0 in this equation. And if I do that, this sort of, the left side of this equation is going to be equal to 0. And I'm actually just going to focus on this for a second. I'm going to focus on the first two parts. So it's going to be 0 equals y plus 4 over 3. So essentially the t value I chose for this equation is 0, because remember, each one of these equals a t value. So I can just now solve for y, and in this case y is just going to be equal to negative 4, right? Because I just cross multiply that 3 by 0, move the 4 to the other side. And then I can do the same thing for the z coordinate. That's also going to be equal to 0, right? So 0 equals z plus 1 over negative 5, which is going to give me z equals negative 1. So the point on the line, oh, I messed up here. Sorry. Nobody caught that. Maybe you did catch that. Oh, I can't erase. Now let me erase. There we go. X equals 5. I plugged in 5 for x, not 0 for x. The t value that came out was 0. So the point that I got on this line was 5, negative 4, and negative 1. Right? So that is a point on this line. And you can do that with any x value. You plug in any x value. You find the t value and then apply it to the other ones to find another point, or the y and the z coordinate, I should say. So that line, if the lines are collinear, this point should also be on this line. How can we check that? Well, we can just plug in this point into this line and see if everything works out. Let's try it. So 5 plus 1 over negative 4 equals the y is negative 4 minus 1 over negative 6 equals z is negative 1 plus 3 over 10. And we can just simplify. So that's 6 over negative 4. So that's 6 over 4 is negative 3 over 2 equals, then we'll plug in our, or we'll just simplify this, negative 5 over negative 6, or just 5 over 6 if we simplify. And then this one is 2 over 10, which simplifies to 1/5. So regardless of whether it's simplified or not, what do you notice about these three values? Obviously, they're all different. So similar to the other question we did where we were checking if a point's on a line, these t values are all different. Remember, these are just t values. The t values are all different. For any point on the line, the t values need to be the same. In this case, to generate this point, the t value was 0 for this line. The t value could have been different for this line, but they have to be the same for all 3 points, for all 3 coordinates. So we know the lines are not collinear because this point is not on this line. So there's the solution.